So let me also start out by thanking the organizers for the invitation and also for putting us up together with Misha in the session, since what I'm going to talk about is closely related. It's basically also on this theme of spin-photon quantum interface. Though, as you will see, I will pursue a slightly different, or I'll show you experiments pursuing a slightly different direction and slightly different applications. So let me, let's see if this works. So, yeah. So to motivate what I'm going to tell you about, I'd like to start by reminding you that entangled quantum systems exhibit correlations that are stronger than what is possible in local realistic classical theories. And it is this feature, or entanglement, that is at the heart of many quantum information, communication, or computation protocols, and is celebrated as a new resource. But one has to be careful, and this comes to the question of quantum control, because actually quantum entanglement occurs in a very mundane, everyday manner in quantum systems. The problem is that typically entanglement occurs without our sort of desire between a quantum system that is of interest to us and other degrees of freedom or other quantum systems over which we have no control. So if this is the case, this entanglement is no longer a resource, it's a problem. It's what we refer to as the coherence, and it is at the heart of emergence of classicality or classical behavior of quantum systems. So to be able to use entanglement as a resource, what is really needed is to be able to control the entanglement process and generate it in between quantum systems over which we have control, meaning that we can carry out measurements and verify and the existence of entanglement as well as to use them. So the goal, or the way we go about generating entanglement, at least in this case, I'm interested in generating entanglement between distant quantum objects. So objects for which application or using a coherent interaction is no longer possible because of the finite range of the forces that upon them. So remarkably, there is a way in this case to generate entanglement, and this relies on the first, in a sequential process, the generation of entanglement between a quantum system and a propagating photon. And one can then use this propagating photon at a different, or take it to another site, let it interact with another quantum system, and use this sequential interaction to generate entanglement between distant objects which have never interacted with each other. So this actually is interesting in its own right, but it also has applications which has really motivated the research on it. And this is mainly quantum communication or long-distance quantum communication research, where the idea is to be able to communicate with perfect security between distant nodes. So again, the issue is that if you have entanglement, we can achieve this at these two distant locations, but we cannot generate it in the usual way. So the method of preference, at least up until now, is really what I will refer to as the heralded probabilistic generation of entanglement. So basically, the resource, as I've been telling you for this, is single photons that are quantum correlated with the emitters that have generated them. So I'm considering basically a stationary quantum system, which in the simplest setting would be a spin, a confined spin, whose wave function in general, if it's non-entangled, that is, a superposition of the two spin orientations, and then a propagating photon pulse, which could be in a superposition of a number of degrees of freedom. So it could be a superposition of the polarization, it could be a superposition of the emission time, or it could be a superposition of the color of the photon. And that's actually the degree of freedom that we use in some of our experiments. Now, as I said, what is really needed is that the spin, the quantum system, is entangled with the photon that it has generated. So here is an example of a resource state, a maximally entangled spin-photon pair that one can use for the purposes that I'm going to tell you. And I'm also going to show you how this state can be generated with relative ease in solid-state systems. But it is also interesting and was recognized early on that this is definitely sufficient, but not a necessary situation. So you can actually generate the task, if you're willing to wait a little bit more, by starting out with vanishing the small entanglement. So basically, even if you start out with the state where, let's say, you have a superposition of spin up and zero photons and a very small probability amplitude for flipping the spin and generating a photon, then this is sufficient to generate heralded entanglement, where the spins would be maximally entangled, even if you start out with vanishing the small entanglement. So there are a number of requirements one has to fulfill to get there, and this is what I listed here, and I'll try to go through these one by one, and some of which Misha actually already mentioned. So basically, in a nutshell, we need single photon pulses. So this entanglement, if it is taking place with a photonic pulse with many photons, then it is quite likely that we will lose these photons and thereby the correlations, because we'll get entangled with other degrees of freedom which we do not have control over. The photons for the protocols that at least we know and that we try to implement have to be indistinguishable. And I'll try to show you what indistinguishability means and how one can verify experimentally that the photons are indistinguishable. And we certainly want coherent spins, and that's one of the, let's say, limitations of the solid-state approach, that the coherence times are relatively short, because once you generate the entanglement, you want that entanglement to survive, which is only possible if the coherence is long-lived. And again, for all this to happen, and in reasonable timescales, one needs an efficient spin-photon interface, meaning that it is nice to have fast emitters, if the emitters are not fast, to enhance the emission rate, for example, via Purcell effect, as Misha was telling you, and also to engineer the photonic environment such that the photons are extracted with high efficiency. And this is important, particularly important in high dielectric media, or the emitters that are embedded in high dielectric media. And this is a connection, let's say, to the topic of this conference, although at a relatively basic level. Okay, so this is the outline of my talk. So I'll tell you about single photon sources sources of indistinguishable single photons, tell you about experiments showing entanglement between a photon and a spin, then the heralded entanglement at a relatively high rate of distant spins. Distant in this case is spin separated by 5 meters. And in the last part, I'll show you some recent experiments on a new material system, which actually holds quite a bit of promise in overcoming some of the shortcomings of the gallium arsenide-based systems that I will first focus on. So with that, let me also say that so if you want to use solid state as single photon sources, this definitely brings in certain advantages like fast emitters, integrability, not having to worry about confining your emitters, but it also brings up issues with the coherence times, this is particularly true in semiconductors. So there are different classes of emitters, and Misha mentioned to you a deep defect in an insulator in diamond. I will be talking about shallow defects in semiconductors. And even though the physical properties are different, many of the concepts are basically applicable to all these 3 different classes. So let me then start out by briefly telling you about quantum dots. So a quantum dot is a mesoscopic semiconductor structure containing anywhere from 1,000 to maybe 10 to the 5 atoms, and that is surrounded by either vacuum or by a semiconductor of a different band gap. So I have two pictures here. The first one is an MB-grown indium gallium arsenide quantum dot that is surrounded by gallium arsenide. So this is the workhorse of, or has been the workhorse of our experiments in my group. And this is another example. Well, it is not really a quantum dot as seen here, but basically the quantum emitters, one should say, occurring because of defects in monolayer two-dimensional structures. And in this case, the structures will be dealing with our tungsten diselenide monolayers. So this is the part, the type of material that I will tell you about later. So now, quantum dots have the nice advantage that because of their relatively large size and integrability in electronic sort of structures or electronic control, one can control the charging state, something you cannot do with atoms, at least not with ease. So if you have a neutral quantum dot, then this is an excellent source of very bright source of single photons. So basically what we can achieve in our group with relatively modest cavities, about 10 million counts per second extraction of photons from a quantum dot. And the experiments that I'm going to tell you are all resonant excitation and looking at photons emitted in resonance fluorescence. And in some experiments, this will be Rayleigh scattering. In others, it will be Raman scattering. Now, if we inject an electron into the quantum dot, now we have an additional degree of freedom, the spin of this electron. And in essentially most of these materials, the light scattering from the spins is strongly correlated with the spin state. This is a consequence of spin-orbit interaction, which is strong both in gallium arsenide as well as in, actually even more so, in the transition metal dichalcogenide structures, semiconductors that I will touch upon. So this is then, in a sense, the resource that one allows to correlate spins with photons. It is really spin-orbit interaction that is responsible. Okay, so the first question is the single photons. I mentioned to you that it is important that the source that we generate contains a single photon, such that provided that we don't lose the photon, in which case the whole protocol fails, then we can be sure, at least the prerequisite is satisfied, that we can avoid correlations with other physical systems. So how one verifies that one is dealing with a single photon source is to carry out Hamburg-Brown twist type photon correlation experiments. Misha already showed you results from atoms and NV centers or silicon vacancy centers. So I will go relatively fast here. So if you do such a measurement, take a photon stream and send it to this correlation setup, but do so with coherent sources of light, then all the pulses that you get in the output will have the same amplitude, saying that photons are uncorrelated if you're dealing with the coherent light source. But if you send in a single photon source, and this is now an experimental data from the Paris group, you can make sure that the two photon events are completely eliminated. Okay, so still most of the time in this case, the pulses are empty, you don't detect anything, but you basically, to a high degree of accuracy, you never detect two photon emission events. And this has become almost a standard sort of starting tool in characterizing single quantum emitters of any sort in the solid state. But this experiment itself only tells you that you have a single photon, not that it has correlations with other degrees of freedom. Okay? So that is actually possible. To avoid this possibility, one has to show that the photons are indistinguishable. That is, if you prepare two photons, that there is no way, other than their propagation direction, to tell the difference between the two photons. If that is the case, you can use a beam splitter, and at the output of the beam splitter, if these two photons are truly distinguishable, have the same spatiotemporal profile, polarization, et cetera, then a detection event here, you will not be able to tell if the photon came from this port or the other port. Okay? And there's a wonderful interference effect called the Hongou-Mandel interference, which tells you that if this is the case, and if you send 2 photons, then the result is that either both photons go to one detector or both of them go to the other detector. And this actually is, of course, true for any bosonic particles. And this allows you, in turn, to measure, look for the coincidences, which will then tell you that the photons have distinguishability. So this is an experiment we did with 2 quantum dots in different cryostats. So if we make sure that the photons are essentially indistinguishable, but change the polarization of one such that they're rendered distinguishable, then we have a center peak here that is half as big as the others, which is precisely what you expect if there is no interference. And if it render the polarizations identical, this center peak becomes about 10% of what it was otherwise. So in that sense, there is a high degree of indistinguishability between photons, which is another essential element if you want to erase the witch path information in the system. Okay, so now let me tell you about this relative, conceptually very simple spin-photon entanglement. So this is the energy level diagram. I will not go into details, but take my word for it that has been verified in many labs. If you have a charged quantum dot, a single electron, then the initial states of the system are designated by the spin of the electron. And then you have 2 optically excited states that are, again, non-degenerate if you apply a magnetic field. So the idea is that you apply a laser pulse, ideally a pi pulse, that excites one of these excited states. And as this excitation decays, it can either emit a red photon to go down to spin-down state or a blue photon to go down to the spin-up state. And unless you look at what the color of the photon is or what the energy of the polarization of the photon is and so on, you cannot tell which of the 2 processes have happened. So you just wait, and you know that spontaneous emission is going to take place. So after you wait, you know that the final state of the system is a maximally entangled state where the spin and the photon color and the polarization in this case are maximally correlated. Okay? So, and these experiments actually were first done by Chris Monroe in trapped ions, then by Misha's group using NV centers, and also by Yamamoto and Steele groups in quantum dots simultaneously. Okay, so how you verify it, and this is part of the interesting element here, that the whole repetition cycle of entanglement generation in our case was 13 nanoseconds. We could even make this shorter. And this is, in a sense, the main advantage of the solid-state system. If you were to do this in an ion, the timescales would be microseconds to a millisecond. Okay, so everything is fast, not just the emission, but also preparation in the solid state. So basically, we first look at classical correlations, meaning that whether it is really true that a spin-up says that the photon is blue and spin-down says that the photon is red. And so first, we do not look at the spin and look at the pulses, the red and blue pulses generated by averaging. And we see that they're identical. This is basically saying that these 2 paths have the same amplitude. Okay? Then we control the photon correlations, indeed make sure that we are dealing with single photon at a time. Then we look at conditional measurements. That is, if we measure the spin to be in down state, what is the color of the photon? And here you see that in those cases, cases, that indeed the photon color is predominantly red. And of course, it's the opposite if we only look at the events in which we measure the spin to be in a spin-up. Okay, so this tells us that indeed there is these correlations, but classical correlations between spin and the photon. So to show that there is entanglement, one has to look at a different basis. So to do that, we actually rotate the spin and measure the spin to be and project it either into up plus down or up minus down. So in our sort of color qubits, what measuring the spin in up plus down means that we project the photon into superposition of 2 different colors. In this case, the colors differ by 5 gigahertz. And of course, what happens in this case is that the photonic, these 2 components speed, leading to oscillations in the detected coincidences. And these oscillations, which actually change phase, if we look at the other projection, tell us that the spin and photon are entangled. Okay, so let me then go to the next set of experiments, which is entanglement of distant spins. So in this case, we use a slightly different protocol, which was first proposed by Cabrillo, Sirac, and Zoller, and was promoted as poor man's entanglement. That is, if you really don't have access to interactions, can you still generate entanglement, but with the price of it being probabilistic. So the idea is this, that you have two spins in two different cryostats, two different quantum dots. You prepare them, say, both in a spin-down state, and then apply a weak pulse. Weak meaning that the light scattering induced by this laser has a very small probability. So say less than 10% chance that a photon will be scattered. And then you take the two sort of probability amplitudes for these two photon pulses, mix them in a beam splitter to the extent that the photons are indistinguishable. When you see a click on one of the detectors, you have no way of saying if it was this guy, this spin that has emitted the photon, or the other one. And this is the basic idea of the spin-photon entanglement. So in our case, what we did is we worked with heavy holes in semiconductors, and I should have mentioned that here. So you see that these oscillations decay in nanosecond time scale. This is something we understand, that the electron spin in quantum dots have a very short T2 start time, and this is a consequence of their interactions with the nuclear spins. One can, in principle, use echo or decoupling techniques to prolong this to microsecond timescales, but in the absence of that, the coherence times are very short. So to be able to generate entanglement at a large distance, we need to maintain the coherence. And that is possible if one uses heavy holes, because of the fact that these have p-type orbital, formed out of p-type orbitals with weak hyperfine interaction. So what we do is that we excite the quantum dot, get the electron out, and in this way optically prepare this metastable state in which the ground state or the metastable state is designated by the Hall spin. Then we do this weak excitation of both of the quantum dots. So the end product of this is that we have a product state, but each quantum dot has this minute amount of entanglement between the spin and the photon number that it has generated. And once we have the click, we can rule out the most likely of these contributions, which is that no photon scattering has taken place. Since we have detected a photon, then the dominant contribution to our state is this maximally entangled spin state. So that's the idea. Just to show you that Hall spins indeed have long coherence times. So we measure using Ramsey interferometry coherence times up to 250 nanoseconds. So more than 2 orders of magnitude longer than electron spins. We can actually also measure the spin coherence using Raman scattering. So this is something that is kind of neat because it really uses some basic quantum optics, which basically tells us that if you look at Rayleigh scattering, so we forget about incoherent light emission, but really only look at scattering processes, which are relevant if you have weak excitation. Rayleigh scattering coherence is determined by the coherence of the laser that excites the system. Okay, so it has nothing to do with the line width of the transition that you are dealing with. With Raman, it's actually the laser coherence plus the spin coherence that determines the coherence time. So if you make sure that your laser coherence is long, then you can use the interference of Raman photons to determine what the spin coherence time is, or at least in this case, to make sure that the spin remains coherent for the time scales that are of interest to us, which is on the order of 20 nanoseconds. Okay, so the photons have to be indistinguishable, that I told you. So we indeed take these two photon pulse probability amplitudes and look at the coincidences and see that the indistinguishability is 90%, so which is not going to limit us. So then we measure the classical correlations, and maybe not as clear as the previous case, but clearly we have a high sort of visibility or high fidelity for essentially having only one of the spins flipped. And then we look at the quantum correlations and the presence of oscillations, even though with modest visibility, is telling us that we indeed have entangled the two spins. Okay, so in the remaining time, I'll talk to you about this promised sort of new semiconductor system that is of interest not just to optics, but also transport community. And that's probably why what makes it really all the more interesting, because I think for the first time, we have a material system where we can really combine optics and transport experiments in one system. Okay? So why is this here? So why am I talking to you about this system? So the first element is that we expect the spin coherence in this system to be substantially longer than gallium arsenide. And there are already a recent preliminary experiment showing that this is the case. And the reason is twofold. First of all, one can, so the dominant isotopes of the elements of both the transition metals and chalcogenides have zero nuclear spin. So it's in principle possible to have a nuclear spin-free material. The other property is that spin and valley are locked into each other due to strong spin-orbit interaction in the system, which requires that spin flip can only take place with, in addition, a valley flipping. So that reduces the likelihood that this will happen. So these systems exhibit very strong optical coupling, as actually first demonstrated by Vino about a year ago. And this allows for embedding in microcavities, open cavity structures. And one can imagine that because of the two-dimensional nature of the system and strong optical coupling, one could make quantum dots in a fully controlled manner in the system. So let me show you briefly what this material is about. It's basically a graphene-like system. It has an effective honeycomb lattice structure, but it has a strongly broken inversion symmetry, meaning that the two inequivalent sites, A and B sites, are occupied by different atoms. So basically, one site has the transition metal, the other site effectively, this is a tri-layer system, so they effectively has two chalcogenide atoms. Okay? So the physics takes place again in the K and minus K values, but because of the inversion symmetry breaking, there is a band gap. And the system is a direct band gap semiconductor where the two bands, actually in this case, remarkably, are mainly the d orbitals of the transition metal. So if you do spectroscopy, excite the system, and look at the photons that come out of it without any electrical control, this is kind of state of the art, at least for us. Really narrow lines, down to 5 milli-electron volt line width. The radiative lifetime should lead to a line broadening of about 1.5 milli-electron volts. So in that sense, even though the lines are broad compared to gallium arsenide, they're really comparable to the radiative lifetime. And we typically see two peaks, the exciton and the tryon is a consequence of the inevitable presence of electrons in the system. So what we did is that we took such a flake, a monolayer, and placed it inside the fiber cavity, an open cavity structure formed out of a dielectric DBR on one side and a curved fiber mirror coated with the same dielectric on the other side. And what we see is that indeed the modes split, so there is normal mode splitting. This is sometimes referred to as strong coupling, but it is different than what Misha was telling you, because this is basically coupling of two harmonic oscillators. Nevertheless, it's showing you that there is indeed very strong optical coupling in this material system with the splitting on the order of 20 millielectron volts, about factor of 5 larger than that of gallium arsenide. These other lines are the higher transverse modes that are associated with the fiber cavity. Okay, so this is a cross-section showing the lower polariton, upper polariton, plus the higher transverse modes. So optical coupling is nice and strong. Now, if this was in molybdenum diselenide, if you go to tungsten diselenide, we accidentally ran into something interesting. There, the spectrum is a lot dirtier than what I showed you earlier, right? So this is a very clean two-peak structure. So in tungsten diselenide, the exciton peak is relatively weak at low powers, and the spectrum is dominated by a red shifted broad feature. And this feature at very low powers develops very sharp peaks, and it is these peaks that are not resolution limited but relatively narrow that motivated us to ask if they can be associated with quantum dots or whether they exhibit quantum light emission. And indeed, this is the case that we looked at a number of these peaks, and practically all of them exhibit anti-bunching. Not perfect, as we have in in-gas quantum dots, and the lifetimes are remarkably long. So the nature of these dots is, we still do not understand. But what is really interesting, in my opinion, is that we do not have to rely on these defect-induced dots, but really engineer them ourselves. Okay, and to sum it up, so it's not just these advantages over gallium arsenide that makes this material system interesting. There's also interesting new physics, and that has to do with the non-zero Berry curvature that these materials have that comes about as a consequence of inversion symmetry breaking. So what I would like to point out here, so there is no experiment, is the comparison between a 2D hydrogen atom and the excitons in such a material as TMD. So first thing is that in hydrogen atom, as you know, the binding energy is 13 electron volts. Here, the binding energy is on the order of 0.5 electron volts. So we're really talking about 2 orders of magnitude higher binding energy than that of gallium arsenide, which opens up possibilities for really exploring the fine excitonic structure. Now, the really nice thing is that there are 2 aspects. The first one is that screening is very special in this material system. So basically, for strongly bound excitons with Bohr radius on the order of 1 nanometer, so all the electric field lines are effectively screened by the material. If you go to higher excitonic states, which have a larger Bohr radius, then the screening becomes less effective. And this has been predicted for the last at least 5 years, and this results in actually the Coulomb interactions describable as with the logarithmic function, and results in this deviation from the hydrogenic spectrum. So the 2 manifold, for example, has a much stronger binding because of the reduced screening as compared to the n=1 manifold. But that's not what I would like to draw your attention to. The really interesting thing, in my opinion, is that if you analyze the system carefully, you find that the 2p orbitals actually are split. And the splitting is a direct consequence of the Berry curvature in the system. That is, we have a system in which the electrons in, say, in K valley, rotate in the counterclockwise direction. And this rotation actually couples to the excitonic states that also have rotation. And basically, whether you are co-rotating or counter-rotating results in a different energy and a different energy splitting for the 2p plus and 2p minus states. Naturally, the time reversal symmetry is preserved, so the splitting is reversed in the minus K valley, but nevertheless, one should be able to monitor this or determine this by using polarization resolved spectroscopy. So this is the first example of a direct signature of Berry curvature in optical spectrum. So as you may know, this is mainly discussed in transport in terms of leading to Hall effect, and has been observed in optical systems by introducing either artificial gauge fields or using spin orbit as an effective gauge field. But the interesting thing here is that it's really the band structures Berry curvature that results in the splitting. Okay, so with that, I will just conclude saying that, that the solid-state systems offer unique advantages as well as problems, mainly in terms of the spin coherence, which we see as a challenge, and we look for ways to overcome them and celebrate the new physics that come up along the way. Thank you. Yeah. So, so basically about lifetime, I'm not sure. Vinod's question is about the valley coherence and the circular dichroism in these material systems, which I would say, in a nutshell, it's an open issue. So it's really remarkable that if you look at a dirty material like tungsten diselenide or molybdenum disulfide, there is a sizable degree of circular dichroism or even valley coherence. That is, by exciting an exciton in using linear polarization, you actually generate a superposition of two excitons, of an exciton in two different valleys. Okay? And this coherence, you can measure how well this survives by looking at the preservation of linear polarization. And this seems to be relatively well preserved, or above 50% in this material system. But if you look at the cleanest system, the molybdenum diselenide, there is practically no is circular dichroism. So this is kind of open as far as I know, and at least I do not have an answer.
Can I also ask a question? So there's obviously a lot of excitement regarding transition metal halogenide, but there are also sort of old excitonic systems like fluoride, also zinc blend system, and also with very nice excitonic lines. Why people forgot about them?
So I don't know. I mean, what I can tell you why I find this material system interesting is because of the ability to actually, or the ease with which one can isolate monolayers, make heterostructures, couple them, place them inside cavities, and hopefully use electrical gates or other mechanisms to define quantum layers. I'm not sure if it's possible in other material systems. The question regards the need to have weak laser pulses for generation of entanglement. And the reason is this. Actually, this is in general not a requirement. So there are protocols, for example, what was realized by Chris Monroe in ions or Ronald Hansen in NV centers, does not require weak pulses. But in that case, you need experiments to make sure that you indeed have sort of ruled out, let's say, both spins having flipped to the undesired state. So the idea here is this, that you need this pulse to be weak to make sure that the probability amplitude for both spins to be flipping is small, is much smaller upon detection. Once you detect the photon, you get some information about the system, right? So you have to update your description. The first way in which you update is that you rule out this component that has the highest probability amplitude, which is that no scattering has taken place. Then you renormalize the remaining wave function, which basically tells you that you have a possibility of either this flipping or the other one flipping, and then there's a finite probability amplitude, which is epsilon square, for both of them flipping. If that were the case, which would have a finite probability amplitude if I had a strong pulse, then I would reduce my entanglement fidelity. So in this way, I sacrifice efficiency or the success rate for the quality of entanglement. Okay, so that's the easiest way of thinking about it.
Another question? Yes, with the last question.
So in high-cal oxide materials, alluded to the fact that spin coherence might be protected by the fact that it's coupled to the valve. And I wondered if you would say, so would this be really kind of a T1 spin protection or a T2 type spin?
So that's a very good question. I guess clearly the T1 protection is extremely strong without the need for a magnetic field. But for T2 or T2 star protection, I would argue that the more interesting line is the fact that nuclear spins should be much less of an issue. Although, again, the dots would be small, so probably the situation would be similar to NV centers, which is, in a sense, the best scenario, because if you really have few nuclear spins, then one or few, then they become, instead of becoming a problem, they become a resource, as Misha and his collaborators have shown.
Then we shall thank both speakers this morning for starting.